So now we come to a third method of differential equation solving, okay, a third form of differential equations that you might see. And the method we're going to use is utilizing an integrating factor, okay, and well, we'll get to that in a second. But firstly, an important part of any of these forms of differential equation is how it looks, okay, how to recognize one. Okay, and this one's going to be when you have dy by dx plus p of x times y, so that's some function of x times y, equals another function of x, we're going to call q of x. Okay, and to start to understand how this method works, you might spot, firstly, that what we have here on the left-hand side doesn't look a million miles away from what you get after differentiating something with the product rule. Okay, because you have a y and a dy by dx, so its derivative. Well, if you had p of x, if you had something here where p of x was its derivative, then that would fit the product rule. Okay, which is a bit of a stretch right now, but it'll make sense soon. Okay, and the way we're going to sort of force this product rule situation is we are going to put something with this dy by dx. Okay, and that's going to happen by multiplying every term, in fact, by what we're going to call I of x, which is the integrating factor. So you can see that every term, left and right hand side, has been multiplied by I of x, sort of to keep it consistent. And, well, it still doesn't look perfectly like the chain rule, the product rule, sorry, and unless this is the case, okay, unless I times p, I of x times p of x, equals the derivative of I. Okay, so if we have this here and its derivative was equal to all of this here, then we would have the result of a product rule, if you will. Okay, so our task now is to find what does I of x need to be for this statement to be true. Okay, which is pretty much like solving for I of x. Now, if for a second we just rearranged it as so, okay, dividing both sides by I of x, okay, then what we're going to do is we're going to integrate both sides with respect to x. Okay, I'm going to integrate both sides. Okay, and right now I don't know what p of x is, so I don't know what this integral is going to be. However, what I do see is that I have on the left hand side I of x and its derivative on top. Now this feels very familiar, okay, because it's quite similar to the U substitution method, okay, integration by substitution. And well, if we called I of x u, then I dash of x would be du by dx, okay, and if we did our full substitution method, we would end up with this on the left hand side, okay, that ln of x, ln of I of x, sorry, would equal the integral of p of x, which we still can't figure out right now without some information about p of x. But if we use our sort of definition of logs for 1 second, then what I can find is what I of x equals. Okay, and that was our goal in the first place. Okay, to find the I of x that would make this thing true here, okay, that would give us the result of a product rule over here on the left hand side here. Okay, so we've kind of found that even though e to the power of the integral of p of x looks quite tricky, well, we found something that's going to work. All right, so based on what we just said, based on the fact that this must be the derivative of I of x, what I'm going to say is that this left-hand side is the derivative of I of x times y. All right, that's how the product rule works. Okay, it's when you're doing the derivative of one function times another. And, well, we know that we've kind of done the product rule in reverse. We know that it would equal what we have above on the left-hand side. Now, that's all well and good, but this still doesn't look particularly solvable. So, well, let's just rearrange that a little bit to get this here. And this starts to look a bit more like a separable equation. Okay, and I can indeed integrate both sides, but in fact I'm going to remove the I of x from the integral, okay, because with respect to y it is just essentially a constant. Okay, so that's almost like the I of x times the integral of 1 dy with respect to y. Okay, so that 1 will become y. Okay. So I've done that integral now, and I have still not done this integral, and, well, I can't yet, without knowing what q is, or without knowing what p is. And in fact, I'm just going to divide both sides by I as well, I of x. And, well, this is significant now because I have y equals. And simply, if I have y equals, I have solved this differential equation. Okay, that's what solving a differential equation means, is getting the function of y in terms of x. Okay, that fits the original differential equation. Okay, but in the thing you were given at the start, you were just given p and q. So this answer doesn't seem to really work unless you know what I is. Okay, and I is in terms of p. Okay, so if I substitute out I for what it equals in terms of p, well then I can go right from the start, right from any given differential equation in this form, okay, and just fill out this almost little formula here. Okay, it's not particularly nice formula, as I've said a few times, but it is a formula that is complete, okay, and one where I can take p and q and just put it all into this formula and should be able to come up with a solution, y equals something in terms of x. Okay, so obviously we do need one example here, because, well, that's probably a lot more of a complicated method than anything we saw with homogeneous or separable equations by themselves. Okay, so let's see this example here. First step on any differential equation, so what form is it in? Now obviously this is a integrating factor video, so this is an integrating factor one, but it doesn't look like it yet unless I divide every term by x. If I divide every term by x, well, I'll have this here, and now suddenly, yes, it is in the correct form. Okay, my p of x is going to be 2 over x. My q of x is going to be this here, and I of x, well, that's e to the power of the integral of p, so that's to the integral of 2 over x. Okay, next. I don't have to do this whole method, okay? I can, in fact, jump straight to this when you're actually solving in an exam. Okay, so y equals 1 over I times the integral of I, again, times q. Okay, so next I might actually want to do the integral of 2 over x, okay, and that's 2 times the integral of 1 over x, and that is 2 times ln of x. Alright, now if I want to put that into I and try and simplify I, well, that's e to the power of ln of x, which is e squared, which is, I can move this 2 up here by one of my log rules. Okay, and e to the power of ln of anything is just that thing inside the log, so x squared. Okay, by one of our more complicated log rules. So in fact, I is x squared. So I'll replace those two things. Okay, and I will also simplify what I have inside that integral there. Maybe I'll just write x to the power of minus 2 for that as well. X times e to the power of x squared. And so now all we have to do is perform this integral, evaluate this integral. And what we see is that I have an x squared and an x, which is half of the derivative of x squared itself. So this looks like a substitution problem. Okay, so if I call u x squared, then du by dx equals 2x. Okay, so x would equal half du by dx, whichever way around you like to do your substitutions. You are going to get something like, if we take this half out the front, it's going to be e to the power of u, which stays the same essentially, and then we substitute back and we'll get e to the power of x squared plus c. Okay, and well, that equals 1 over 2x squared times this bracket, which you could expand, maybe not completely necessary, but we'd have this, and we can't ignore the c in this situation. Okay, and this would be your solution to the differential equation. Okay, so easily the sort of more complex method out of the 3 you had to learn in HL, A&A calculus. So one that you should practice a few of, but well, you can, as I said, jump these steps in the theory that we went through there. So it's just a little bit long, but nothing too tricky in the end. Okay, so good luck.